Alright, for the fourth lab, we looked at the magnetic field of a bar magnet. Broke this lab report into four sections. I'm gonna first introduce some of the fundamental principles, look at the results, we'll look at the computational model, and finally do a discussion of the overall principles. Starting off with the introduction, some more broad things to keep in mind that I'm trying to get to understand here is understanding the fundamental properties of bar magnets, and how they generate magnetic fields, exploring the mathematical and physical behaviors of dipole magnetic field along its axis by applying things like superposition, using computational models to do visualization, and just using approximations and using those comparisons. Some physical properties that we take advantage of, or the physics, is the relationship of the magnetic field of a bar magnet, with K being a proportionality constant, and the magnetic field being dependent upon R, and N being the portion the rate of decay and determining the rate of decay. There's an on-axis approximation as well as a logarithmic form that can be used to derive a linearization and a relationship, as well as just a general magnetic field of a dipole. The net magnetic field was calculated at the points labeled in yellow there, the yellow circles, using experimental data obtained in lab. The results were compared against a computational model that we'll discuss in a moment. So the data attained, this right here is just the raw data, and this graph was plotted. Note at the bottom is the net magnetic field at the location 45 degrees from the dipole. This data was used to perform some calculations. Right here is just derivation of a symbolic expression for mu, and just using some of the data from the ln of b versus ln r graph, we were at an estimation for mu of 3.206 newtons per meter was obtained. So we determined that only the first and last observations were true. That when the magnetometer is far away from the magnet, you get a near zero field in the x direction, and as they move closer, the x component of the magnetic field increases. The computational model took advantage of the equation for the dipole magnetic field. Two on-axis magnetic fields were produced, vectors, and whereas four perpendicular ones. And right here is just the code generating those arrows. And finally, right here generates another off-axis vector at a 45-degree angle from it. Here is the model produced, with the cyan being the perpendicular vectors, the orange being the on-axis, and the magenta being the 45-degree. Note that in the bottom right is the text returned by the program, and it returned the magnitude of the magnetic field at that distance. This distance, or this value, this magnitude, was compared to the theoretical, and determined that it was the same order of magnitude, which was considered acceptable given the context of the experiment. And so, to wrap it up, to discuss some what if scenarios, if we had oriented the experiment to compensate for the magnetic north, and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field, your results would have changed. And then, if you were to stick two identical magnets together end to end and run the experiment again, how would you expect your measurements to differ? You would expect the measurements to differ by some intermediate magnitude and some intermediate angle in order to get some intermediate amount. As